Plate tectonics and how the Earth works. The outer shell of the Earth is broken into plates. These plates move about the Earth. The interaction at the plate boundaries creates mountain chains, volcanoes, earthquakes, and it changes the face of the Earth over time. This is a perfect example of the Kuhn scientific revolution idea. So science goes about day by day. We're always, scientists are doing science, and then it's punctuated by these revolutions. Plate tectonics is one of these revolutions in science. It's a powerful idea based on multiple lines of evidence. Those multiple lines of evidence were collected over 100 years of collective thought on Earth processes, and then boom, kind of a mind-blowing time, plate tectonics became the unifying theory in geology. It evolved in the 60s and really became textbook knowledge in the 70s. I'm trying to move my face out of the way. There we go. So in 1915, Wegener hypothesized continental drift. And in continental drift, he was able to show the evidence of plate tectonics, but not the mechanism. And it wasn't until the 60s with Harry Hess and Dietz when the topography of the seafloor became apparent, and then they put it all together into plate tectonics, where the plates move, and there's spreading centers at mid-ocean ridges and trenches where crust or lithosphere is recycled. So the evidence was overwhelming in 1968. It entered textbooks in the early 70s. It changed the view of most geologists. People bought into plate tectonics. The unifying theory means it's really started to explain a lot of different phenomena that were kind of half explained before plate tectonics was a thing. Explained environments of deposition and sedimentary rocks. It explained the location of and the variety of igneous rocks. It explained why mountain chains are cored by metamorphic rocks. It explained why earthquakes and volcanoes are found in these linear chains around the Earth. It explained why continents are where they are and how ocean basins work. Really furthered the understanding of fossils, and one set of fossils on one continent and another set of fossils on another continent were maybe related because they were once together, and really explained how mountain chains form. So we didn't really know how something like the Appalachian Mountains formed, and it wasn't until the 70s that that became clear. And of course, explained how the continents could move. Like continental drift, that's fine. It seems like there was a puzzle and Pangea and things fit together, but not being able to tell how they moved really was a barrier to the acceptance of continental drift. Okay, so the lithosphere is made up of the uppermost mantle and the crust. The uppermost mantle and the crust. And the movement of material within the asthenosphere is what one of the ways that the plates move. We'll talk more about that. But the asthenosphere is soft. Asthene means weak. It's the weak layer. It can flow. So looking at the image, if we put a load down on the lithosphere can sink down into the asthenosphere. It bends when it's loaded like that. Buoyancy. So you probably already know that an iceberg, when you see an iceberg, 20% of the ice of that iceberg is above the sea surface, whereas 80% of it is below the sea surface. So that much mass is displaced in the ocean with 20% of the ice above. That is isostasy. An iceberg sinks until the mass of water displaces is equal to the total mass of the iceberg. we are going to use this to think about lithospheric plates. The continents are not very dense, but they're massive, and they can sink down into the asthenosphere a bit, but they do kind of float above the asthenosphere. So the continents float a little bit higher because they're less dense. Whereas the oceanic crust is a denser crust. It's a different rock type. Oceanic crust is basaltic, continental crust is granitic. And so that heavy oceanic crust, even though it's thinner, it's going to sink down into the asthenosphere. Okay, the two types of lithosphere are the continental lithosphere and the oceanic lithosphere. In the diagram, see the crust, the thickness of the continental lithosphere is including the crust and the rigid upper mantle. So that can be an average of something like 150 kilometers thick. The continental crust, here just the granitic crust, this brown layer is 35 to 40 kilometers thick. So just this one's 35 to 40. The whole is 150. It is more buoyant, it's less dense, it's going to float higher on the asthenosphere, and down below that then is going to be the oceanic lithosphere. It's thinner. The oceanic lithosphere, this whole section here, can be 7 to 10 kilometers thick. It just depends. It's going to be very thin at the mid-ocean ridge where it's being created. Out in the ocean, though, the thickness of this crust is 7 to 10 kilometers thick. It's heavier, it's more dense, it's going to sink down into the asthenosphere.